Hi, this is Dr. Bay, and here's Bugsy, and today we're going to go over the mechanism and synthetic use of hydroboration-oxidation reactions.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy. Soaring through the sky, triumphantly we fly, give rise to the complexity of life. Living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Hydroboration-oxidation is a two-step reaction that converts alkenes into alcohols. This reaction was discovered by an English-born American chemist named Herbert Charles Brown in the 1950s, and it was an important reaction because it was the first one that was anti-Markovnikov. His discovery eventually led him to win the Nobel Prize in Chemistry in 1979 for his development of organoboranes in organic synthesis. And organoboranes are especially useful because they can be used for reductions, rearrangements, and additions, which have really opened up a range of new possibilities for linking carbon atoms to one another. In the mechanism for hydroboration oxidation, we'll explain both its regioselectivity as well as its stereospecificity. Its regiochemistry follows anti-Markovnikov, where the reaction installs a BH2 group on the less substituted carbon of the alkene. This reaction is stereospecific because both the H and the BH2 groups add onto the same face of the pi bond, which we'll get into the details later in this video. This reaction utilizes a reagent called borane, or BH3. The structure of borane is actually similar to that of carbocation because it contains an empty p orbital shown in orange. Since the boron atom lacks a full octet of electrons, it's super reactive and is often stabilized by the lone pair of electrons from a solvent like THF or tetrahydrofuran. In the reaction shown at the bottom, THF donates its electron density into the empty p orbital of boron in order to stabilize it. Now let's go over the mechanism of hydroboration oxidation for the following reaction. We're reacting 2-methylpropene with borane in THF in the hydroboration step and hydrogen peroxide and sodium hydroxide in the oxidation step, all to form our final product of 2-methylpropanol. So to help visualize this reaction better, I labeled each of the carbons in green. First, the pi bond in between carbons 1 and 2 react with the boron atom, and then a second arrow from the bond between B and H goes to the more substituted carbon, which in this case would be carbon 2. Then you get the following intermediate where a new bond formed between carbon 1 and boron, as well as a hydride shift onto carbon 2 occurred. This step repeats 2 more times until there are no more BH bonds. Keep in mind that R stands for the alkyl chain, and it's just an easier way to draw our trialkyl borane without drawing all the other carbon chains. Now, in the second part of the reaction is the oxidation step. Hydrogen peroxide reacts with hydroxide ion in a proton transfer. The hydroxide ion acts as a base to deprotonate a hydrogen from H2O2 to form a very reactive hydroperoxide ion and water. Next, there's a nucleophilic attack of hydroperoxide ion onto the boron atom of the trialkyl borane that was formed from part 1 to make the following intermediate. Then a rearrangement occurs where an alkyl group R migrates to oxygen, causing a hydroxide group to leave. Then the first 3 steps of oxidation repeats until the trialkyl borane becomes a trialkoxyborane. In the 5th step, a hydroxide ion acts as a nucleophile to attack the boron atom of trialkoxyborane to form a negatively charged boron atom. In the 6th step, an alkoxide ion is expelled, removing the negative charge from boron. And in the last step, the alkoxide ion gets protonated by water to form our final product. Now, if we included the rest of the R group, this would be our final product, starting from an alkene and ending with an alcohol group at the less substituted side of the alkene. So this reaction follows anti-Markovnikov addition of BH3, where BH2 goes to the less substituted side of the alkene, while the hydrogen goes to the more substituted side. But why does this occur? There are two reasons that can help explain this preference, which are electronic and steric considerations. To help understand this, let's take a look at the transition state structure for both the favorable anti-Markovnikov transition state as well as the unfavorable Markovnikov transition state. When the alkene attacks the boron atom, there's a partial positive charge buildup on the more substituted side of the alkene in the transition state, which thus triggers a hydride shift to occur. If we draw in the partial charges in the favorable transition state on the left, we can see that each of the partial charges line up well, where positive lines up with negative and negative lines up with the subsequent positive charge. However, if we draw the partial charges in the unfavorable transition state, we see that like charges repel one another, since the partial positive charge on the alkene and the partial positive charge on the boron atom are on the same side, which thus is unfavorable. So this means that BH2 must be positioned at the less substituted carbon of the alkene in order to avoid all charge repulsions. Another reason why this reaction is anti-Markovnikov can be explained using sterics. Since BH2 is larger than H, the anti-Markovnikov TS is sterically less crowded and therefore lower in energy than that in the Markovnikov transition state. Notice in the unfavorable TS, there's a steric clash between the BH2, shown in blue, and the alkene substituents, shown in yellow. So recall that in the first step of the reaction, the BH2 group and the H are added onto the same face of the pi bond, which is called syn addition. In the first reaction that we discussed, no chiral centers were formed in the final product, since each of the carbon centers didn't have 4 different substituents around them. However, imagine if we added an additional methyl group to the bottom of the alkene. This would mean that one chiral center would be formed as signified by the squiggle line drawn onto the hydroxyl group. Therefore, both enantiomers in this case would be formed. If we did the same to the top carbon in the next example, then we would be creating 2 chiral centers in the product. All this means is that 2 enantiomers would be formed where H and OH groups are in the same types of bonds, either both on dashes or both on wedges. However, keep in mind that no diastereomers would be formed because syn addition means that both the H and OH groups have to be on the same types of bond. In conclusion, hydroboration converts an alkene into an alcohol group using borane, hydrogen peroxide, and sodium hydroxide. This reaction is both anti-Markovnikov as well as stereospecific.